February 22nd, 1943, near Spitler, Tunisia. As the dust from the Battle of Sidi Bou Zid began to settle over the North African desert, German tank crews from Panzerabteilung 501 approached an abandoned American tank. The vehicle sat motionless on the sand, hatches open, track still intact. Its name, painted in white letters across the bow, read War Daddy 2. The crew had fled during the chaotic fighting that marked the United States Army's first serious engagement with German armor in North Africa. The Germans had won this particular engagement. American forces, inexperienced in desert warfare and outmaneuvered by veterans of Rommel's Afrika Korps, had abandoned equipment across the battlefield. But what the Germans captured that day would challenge every assumption their engineers held about American industrial capability. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This was not just another knocked-out enemy vehicle. This was an M4A1 Sherman medium tank, and it was about to make a journey that would reveal a truth German military planners did not want to acknowledge. Within hours of its capture, Panzerabteilung 501's commander made an unusual decision. Rather than strip the tank for parts or use it as target practice, he ordered his men to drive it. The journey from Spitler to Tunis covered 350 kilometers through desert terrain that had destroyed countless German vehicles through mechanical breakdown. The trip took 4.5 days. The Sherman made the entire distance without a single mechanical failure. German tankers, accustomed to nursing temperamental panzers across North Africa, noted this with growing unease. Their own tanks required constant maintenance. Transmissions failed, engines overheated, track pins sheared under stress. Yet this American tank, captured in the field after combat, driven by crews unfamiliar with its systems, simply worked. When War Daddy 2 reached Tunis, German High Command made another decision. This tank would be shipped to Germany for comprehensive analysis at the Army Weapons Office testing facility at Kummersdorf. The strategic situation in February 1943 demanded this analysis. German forces knew they faced not just Britain and the Soviet Union, but the full industrial might of the United States. American entry into the war had fundamentally changed the calculus of victory. Germany's leaders understood that American factories could produce equipment in quantities the Reich could never match, but quantity meant nothing without quality. German propaganda assured soldiers and civilians that American industry produced inferior equipment, that mass production meant cheap construction, that German engineering remained superior in every meaningful way. The Tiger tank had entered service just months earlier, in August 1942. This 57-ton heavy tank mounted the legendary 88mm gun and featured armor up to 100mm thick. German military leadership considered the Tiger the ultimate expression of armored warfare. A single Tiger could destroy multiple enemy tanks before suffering damage. Its armor could withstand hits that would obliterate lesser vehicles. Surely American tanks, mass-produced by a nation that had entered the war unprepared, could not match German craftsmanship. The Panzer IV, Germany's primary medium tank throughout the war, had been continuously upgraded since 1937. By 1943, it mounted a long-barreled 75mm gun and featured improved armor. German tankers trusted their equipment. They had defeated Poland, France, Yugoslavia, and driven deep into Soviet territory. Their tanks, they believed, represented the pinnacle of armored vehicle design. Then the Sherman arrived at Kummersdorf. German engineers approached the American tank with professional curiosity mixed with ideological certainty. They expected to find evidence confirming their assumptions about American inferiority. They would document the tank's crude construction, its mechanical inadequacies, its predictable failures under stress. Instead, they discovered something that fundamentally challenged German engineering philosophy. The testing began with basic measurements. Engineers stenciled numbers across the Sherman's hull, recording armor thickness and angles with Germanic precision. The frontal armor measured just over 2 inches, angled at approximately 47 degrees. German tanks featured thicker armor, particularly the Tiger. But the Germans noted something unusual. The Sherman's armor, while not as thick as German plate, was remarkably consistent. American manufacturing produced armor of uniform quality across the entire vehicle. There were no weak spots from poor welding or inconsistent tempering. The Sherman's construction revealed American industrial philosophy, where German tanks featured complex hand-fitted components requiring skilled craftsmen. The Sherman used standardized parts produced on assembly lines. Every bolt matched standard specifications. Every component fit perfectly with corresponding parts. A mechanic could remove a transmission, engine, or suspension component from one Sherman and install it in another without modification. German tank production involved extensive hand-fitting. Individual craftsmen adjusted parts to achieve proper tolerances. This resulted in vehicles that performed well when properly maintained by skilled mechanics, but made field repairs difficult. Each Panzer IV or Tiger required parts specifically manufactured for that individual tank. Standardization existed in theory but proved elusive in practice. The Sherman's engine compartment provided the first profound shock. The tank used a Continental R975 radial engine, an aircraft engine adapted for ground use. German engineers recognized this engine design immediately. Radial engines were common in aviation but rare in armored vehicles. The installation was remarkably clean. Fuel lines, oil lines, electrical systems, and cooling systems were logically arranged and easily accessible. Maintenance hatches opened wide, providing unobstructed access to major components. German engineers, who regularly maintained Tigers and Panthers, understood the significance immediately. Tiger maintenance required removing the engine entirely to access certain components. The Tiger's Maybach HL230P30 engine, theoretically more powerful than the Sherman's power plant, was mounted in a compartment so cramped that mechanics worked in nearly impossible conditions. Oil leaks were common and difficult to repair. Fuel system problems required hours of disassembly to reach. The Sherman's engine could be accessed, inspected, and maintained in a fraction of the time German tanks demanded. The Germans test-fired the Sherman's Continental engine repeatedly. They documented fuel consumption, oil consumption, cooling efficiency, and operating temperatures under various loads. The engine ran hour after hour without failure. More significantly, it required minimal maintenance between operating periods. Oil didn't leak, gaskets held. The cooling system functioned efficiently even under sustained high loads. German engineers noted this with professional frustration. Their own tank engines, particularly the Maybach engines used in Tigers and Panthers, were prone to overheating. Gaskets failed regularly. Oil leaks were endemic. The Panthers that had entered service in 1943 suffered catastrophic engine fires caused by fuel leaks. At the Battle of Kursk in July 1943, just months after War Daddy II's capture, brand new Panthers would suffer over 50% mechanical breakdown rates before even reaching combat. But the Sherman's engine was merely the beginning. The transmission revealed engineering choices that challenged fundamental German assumptions about tank design. The Sherman used a manual transmission with a synchromesh system that allowed smooth shifting between gears. The clutch mechanism was simple, reliable, and repairable in field conditions. German engineers tested the transmission extensively, cycling through gears hundreds of times under load. It functioned flawlessly. The Panther tank, Germany's answer to the Soviet 34, used a complex 7-speed transmission manufactured by Zahnradfabrik Friedrichshafen. This transmission featured advanced engineering that provided excellent theoretical performance. In practice, it proved disastrously unreliable. Early Panthers suffered transmission failures at rates that made sustained operations impossible. Even after extensive modifications, Panther transmissions remained problematic throughout the war. Mechanics had to remove the entire transmission from the hull to effect repairs, a process requiring specialized equipment and skilled personnel. The Sherman transmission could be accessed and serviced through hull hatches without removing it entirely. More importantly, it simply didn't fail with the frequency German transmissions did. American engineers had chosen proven, simple designs over theoretical optimization. The result was a transmission that worked consistently under field conditions, rather than one that performed brilliantly on test stands but failed in combat. The Sherman's final drives and suspension system provided another revelation. The tank used a vertical volute spring suspension system with bogie assemblies that could be replaced individually in field conditions. Each bogie was an independent unit, meaning damage to one assembly didn't compromise the entire suspension. German engineers noted that the Sherman could lose multiple road wheels and continue operating. The suspension absorbed shocks from rough terrain without transferring excessive stress to the hull or internal components. German tanks used increasingly complex suspension systems. The Tiger featured overlapping road wheel arrangements that provided excellent cross-country performance but proved maintenance nightmares. Mud, snow, and debris packed between wheels and froze solid in winter conditions, immobilizing entire vehicles. Replacing damaged road wheels required removing multiple other wheels first, a time-consuming process that demanded specialized tools. The Panther's torsion bar suspension was theoretically superior, but made lower hull repairs extraordinarily difficult. The Americans had chosen simplicity. The Sherman's suspension was not cutting-edge. It was not theoretically optimal, but it worked. It worked in North African deserts and Russian mud. It worked in Italian mountains and French hedgerows. Most importantly, it could be maintained by mechanics with basic tools and repaired in field conditions without returning vehicles to depot-level facilities. Testing continued through the spring of 1943. German engineers drove War Daddy 2 across the Kummersdorf proving grounds repeatedly. They measured fuel consumption, operational range, cross-country performance, and reliability under various conditions. The Sherman exceeded German expectations in nearly every category. It climbed slopes German engineers considered impassable for tanks. It forded water obstacles. It operated continuously without the constant maintenance German tanks demanded. The Sherman's fuel efficiency particularly impressed the German analysts. The Continental engine consumed less fuel per kilometre than comparable German power plants, despite propelling a similar weight vehicle. This efficiency translated directly into operational range. A Sherman could operate further from its supply base than a German tank could. In a war increasingly defined by logistics, this advantage proved decisive. German engineers also tested the Sherman's 75mm gun. The M3 gun, mounted in the Sherman, was not particularly powerful by 19 May 43 standards. It could not penetrate a Tiger's frontal armour at typical combat ranges. German analysis confirmed what their field experience suggested. The Sherman was outgunned by German medium and heavy tanks, but the German analysts noted something else. The Sherman's gun was reliable. It fired consistently. The stabilization system, primitive by later standards but revolutionary for 1943, allowed reasonably accurate fire while moving. German tanks lacked gun stabilization entirely. The Sherman's electrical traverse system for the turret worked smoothly. The sights were clear and easy to use. The ammunition stowage was logical and accessible. The 75mm gun might not penetrate Tiger armor, but it could destroy German light and medium tanks, anti-tank guns, bunkers, and infantry positions. The gun itself rarely malfunctioned. When it did, repairs were straightforward. The Americans had created a weapon system that worked consistently, rather than one that performed optimally under perfect conditions. By the summer of 1943, German engineers had completed their analysis of War Daddy 2. The official reports documented armor, thickness, gun performance, and tactical capabilities. These technical specifications were shared with field commanders and used to develop anti-Sherman tactics. But the unofficial conversations among the engineers revealed a more troubling truth. The Sherman was not a sophisticated tank. It was not cutting-edge. Its armor was inadequate. Its gun lacked penetrating power. By German standards of tank design, the Sherman represented compromises and simplifications that theoretically made it inferior. But those compromises created a tank that simply worked. Hour after hour, day after day, the Sherman operated without the mechanical failures that plagued German armor. German engineers understood the implications immediately, even if military leadership could not acknowledge them openly. The United States was producing these tanks by the thousands. The Sherman had entered production in February 1942. By the time War Daddy II reached Kummersdorf, American factories had already produced over 10,000 units. Production was accelerating. By war's end, the United States would manufacture approximately 49,300 Sherman tanks. Germany's entire tank production for World War II totaled approximately 67,000 vehicles of all types. This included light tanks, medium tanks, heavy tanks, assault guns, and tank destroyers. The United States would produce nearly as many Shermans alone as Germany produced armored vehicles in total, and every single Sherman featured the same reliable mechanical systems German engineers had documented in War Daddy II. The Germans confronted a philosophical divide in engineering approach. German design prioritized theoretical performance. Tanks should have the thickest armor, the most powerful guns, the most sophisticated systems. If this complexity made maintenance difficult and production slow, that was acceptable because individual German tanks were superior. Quality would triumph over quantity. American design prioritized reliable production and field maintenance. Tanks should work consistently under field conditions with minimal maintenance. If this required accepting less than optimal theoretical performance, that was acceptable because reliable tanks serving with units were worth more than sophisticated tanks broken down awaiting parts. Availability would triumph over capability. The photographs from Kummersdorf showing War Daddy II during testing reveal this disconnect. German engineers, wearing neat uniforms, examine the Sherman with expressions that historians have variously interpreted as curiosity, frustration, or resignation. They had documented American engineering that worked. They understood the implications. Their own tanks, theoretically superior, could not match American reliability. Albert Speer, Minister of Armaments and War Production for the Reich, personally examined captured Sherman tanks. Photographs show him sitting in a Sherman's commander's hatch at Kummersdorf, experiencing firsthand the American design philosophy. Speer understood industrial production better than most Nazi leaders. He grasped that German industry could not produce vehicles with Sherman-level reliability at Sherman-level production rates. German manufacturing remained rooted in skilled craftsman traditions rather than true mass production. The German military had options for responding to American tank production. They could have simplified German tank designs to enable mass production. They could have prioritized reliability over performance. They could have standardized components across vehicle types to simplify logistics. Instead, they chose to build more sophisticated, more powerful, more complex tanks in smaller numbers. The Panther tank, entering service in 1943, was Germany's answer to the 34. It featured sloped armor, a powerful 75mm gun, and excellent cross-country mobility. On paper, the Panther was superior to the Sherman in every combat characteristic. In practice, early Panthers suffered catastrophic reliability problems. Engines caught fire, transmissions failed, final drives broke. At Kursk, Panthers broke down faster than they were destroyed by enemy action. By late 1943 and into 1944, German engineers gradually resolved the Panther's most serious problems. Engine life increased from 700 kilometers to 1,000 kilometers, and eventually to 1,500 kilometers between major overhauls. Transmission reliability improved to acceptable levels, meaning Panthers could complete road marches without leaving a trail of broken vehicles. But even improved Panthers never matched Sherman reliability. The Tiger tank, despite its fearsome reputation, suffered similar problems. Tigers were expensive to build, requiring approximately twice the production time of medium tanks. They consumed fuel at prodigious rates, limiting operational range. Mechanical breakdowns occurred frequently enough that Tiger units rarely fielded their full complement of operational vehicles. A Tiger that reached the battlefield was devastatingly effective. Tigers that broke down on the march to battle contributed nothing. German industry produced approximately 1,347 Tiger I tanks between August 1942 and August 1944. During that same period, American factories produced over 35,000 Shermans. The numbers told the story. German engineers at Kummersdorf already understood. Germany faced an enemy who could replace losses faster than German forces could inflict them, whose tanks worked consistently, and whose industrial capacity exceeded German production by orders of magnitude. The testing of War Daddy 2 continued beyond the initial analysis. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German engineers used the Sherman as a baseline for comparison with captured Soviet and British tanks. They tested German weapons against Sherman armor. They trained German anti-tank crews using War Daddy 2 as a target. The tank served German purposes for months, running reliably throughout. German mechanics who maintained War Daddy 2 experienced the Sherman's design philosophy firsthand. They could perform routine maintenance quickly. They could access components without specialized tools. They could troubleshoot problems logically because American engineers had designed systems for field repair. These German mechanics, accustomed to the maintenance demands of Tigers and Panthers, recognized the Sherman's superiority in practical terms, even if official reports emphasized German tactical advantages. The Sherman's reliability created operational capabilities German tanks could not match. American armored divisions could move longer distances between maintenance halts. They could sustain operations for extended periods without vehicles breaking down. They could operate further from supply bases because vehicles consumed less fuel and required fewer replacement parts. These advantages translated directly into strategic mobility that German forces increasingly could not counter. By late 1943, German forces were capturing Sherman tanks on multiple fronts. In Italy, North Africa, and eventually in Western Europe, destroyed or abandoned Shermans fell into German hands. The Wehrmacht, increasingly desperate for armor, pressed captured Shermans into service with German markings. These Butterpanzer, trophy tanks, provided German units with vehicles more reliable than their own equipment. The Germans who crewed captured Shermans noted the differences immediately. The Sherman's interior was more spacious than German medium tanks. Visibility from the commander's cupola exceeded that of most German vehicles. The electrical turret traverse worked smoothly, allowing faster target acquisition than hand-cranked systems. Most significantly, the Sherman simply didn't break down with the frequency German tankers expected. German tank crews in 1944 faced deteriorating conditions. Allied bombing had disrupted component production. Critical materials were increasingly scarce. Quality control declined as skilled workers were drafted and replaced with forced laborers. New tanks arrived at frontline units with defects that would have been unacceptable earlier in the war. Panthers suffered final drive failures so frequently that units expected 20% of tanks to break down during road marches. Tigers consumed fuel so rapidly that operational planning centered around fuel availability rather than tactical opportunities. Against this backdrop of declining German tank reliability, captured Shermans represented remarkably capable vehicles. Lucky enough to acquire functioning Shermans used them preferentially for operations where reliability mattered more than firepower. The Sherman's mechanical dependability made it valuable as a recovery vehicle, even after its turret was removed. German mechanics, struggling to maintain temperamental Panthers and Tigers, marveled at how simple Sherman maintenance was. The joke among German tankers was that a Sherman could be maintained with a hammer and determination, while a Panther required an engineering degree and divine intervention. The spring of 1944 brought Operation Overlord. When Allied forces landed in Normandy on June 6, they brought with them thousands of Sherman tanks. German defenders in Normandy included elite SS Panzer divisions equipped with Panthers and Tigers. The subsequent fighting confirmed what German engineers at Kummersdorf had discovered. Individual German tanks possessed superior firepower and armor, but American tanks possessed superior reliability and were supported by superior logistics. The battle for Normandy became a campaign of attrition. German tanks destroyed Shermans at ranges where Shermans could not effectively return fire. Kill ratios in tank versus tank combat favored German armor significantly, but operational readiness told a different story. German panzer divisions rarely fielded more than 50% of their authorized tank strength. Mechanical breakdowns, maintenance delays, and parts shortages kept hundreds of German tanks out of action even when they had not been damaged by enemy fire. American tank battalions maintained operational readiness rates above 90%. When Shermans were damaged in combat, recovery vehicles retrieved them quickly. Repair units close to the front line returned damaged vehicles to service within days or even hours. The American logistics system ensured spare parts arrived before units ran critically short. This systematic approach to maintenance and repair meant that American armored divisions could sustain operations indefinitely. German panzer divisions, in contrast, saw their strength erode continuously. Tanks lost to mechanical breakdown could not be recovered because Panther recovery vehicles broke down attempting to tow disabled Panthers. Spare parts that existed in depots could not reach frontline units because Allied air superiority made daylight movement suicidal. New replacement tanks arrived from factories without adequate testing, suffering immediate mechanical failures when pressed into service. The 501st SS Heavy Panzer Battalion's experience moving from inland Normandy to Villers-Bocage in June 1944 illustrated German reliability problems. The battalion began the movement with 45 Tiger tanks. Only 5 reached Villers-Bocage, an 85% breakdown rate on a simple road march. Those 5 Tigers performed brilliantly in combat, destroying numerous Allied tanks. But 40 Tigers failed to reach the battle because German mechanical reliability could not support strategic movement. American armored divisions moved hundreds of kilometers across France in summer 1944 with minimal mechanical losses. The Red Ball Express, that legendary logistics operation, kept fuel and spare parts flowing to advancing units. Sherman reliability enabled this rapid advance. German forces attempted to conduct a fighting withdrawal, but found their Panthers and Tigers broke down faster than they could retreat. Hundreds of German tanks were abandoned not because of enemy action, but because mechanical failures immobilized them beyond field repair capability. The German engineering establishment watched this unfold with professional horror. Everything War Daddy 2's testing had revealed about American design philosophy was being validated on a continental scale. Reliability, maintainability, and producibility had proven more important than technical sophistication. The Salomiter. Americans had won not by building better individual tanks, but by building tanks that worked consistently and could be produced in unlimited numbers. Albert Speer's armaments ministry attempted to address German production problems through standardization and simplification. These efforts came too late and encountered resistance from military leadership who wanted more powerful, more sophisticated weapons. The Panther's final drives continued failing throughout 1944 despite repeated design modifications. The Tiger II, introduced in 1944, was even more powerful and sophisticated than the original Tiger, but suffered worse reliability problems because its 700 horsepower engine struggled to move its nearly 70-ton weight. German tankers who survived the war and were interviewed afterward consistently mentioned Sherman reliability with mixture of respect and frustration. They knew their Tigers and Panthers were superior combat vehicles when functioning. They also knew those vehicles functioned far less often than Sherman's did. One former Panther commander recalled watching American armored columns advance past his position. His Panther had broken down yet again, immobilized, awaiting parts that would never arrive. The Americans drove past in Shermans that simply worked, advancing into Germany while technically superior German tanks sat disabled. The Battle of the Bulge, in December 1944, provided a final demonstration of relative reliability. German planning for the Ardennes offensive assumed that deep penetration into Allied rear areas would capture fuel dumps necessary to sustain German armor. German tanks began the offensive with fuel for only 150 kilometers of movement. Panzer divisions expected to refuel from captured American supplies. The plan failed partly because of determined American defensive resistance, but ultimately because German logistics could not sustain operations even when breakthroughs occurred. German tanks ran out of fuel within sight of objectives. When fuel was available, mechanical breakdowns immobilized entire formations. The 2nd SS Panzer Division halted after crossing the Our the river, immobilized by empty fuel tanks. The 1st SS Panzer Division abandoned dozens of vehicles after exhausting fuel supplies. German forces lost more tanks to mechanical breakdown and fuel shortages than to American defensive fire during the Battle of the Bulge. American armored units responding to the German offensive moved hundreds of kilometers in winter conditions to reinforce threatened sectors. The Sherman's reliability enabled this rapid redeployment. Units that should have required days to move into position arrived within 48 hours, their tanks operational and ready for combat. The logistics system that German planners thought they had severed simply rerouted supply columns. Fuel and ammunition reached American units faster than German forces could exploit their initial breakthrough. German tank production continued until nearly the end of the war, but quality collapsed along with overall German capability. Late-war Panthers and Tigers suffered from poor quality materials, inadequate testing, and assembly by forced laborers with no incentive for careful work. Some historians have documented sabotage by foreign workers in German tank factories, contributing to the epidemic of mechanical failures in late-war German armor. Whether through deliberate sabotage or merely lack of care, late-war German tanks were even less reliable than earlier models. The Sherman, meanwhile, evolved throughout the war. Later models featured improved armor, better guns, and refined mechanical systems. The M4A3 model with the 76mm gun represented significant improvement over early Shermans, but the fundamental reliability that German engineers had documented in War Daddy II remained constant. Sherman production continued at high rates through 1945, with American factories maintaining quality control even as production volumes increased. The final irony came after Germany's surrender in May 1945. British and French forces captured German tank factories and attempted to build Panthers for evaluation and possible post-war use. These Panthers, assembled under Allied supervision with presumably better quality control than late-war German production, proved so unreliable that testing programs were abandoned. Several caught fire during initial operations. Transmissions failed repeatedly. The Panthers built post-war by Allied engineers failed to match the reliability of Panthers built by Germans in 1943, let alone match Sherman reliability. The lesson German engineers had learned at Kummersdorf in 1943 echoed through post-war tank development. Reliability mattered, maintainability mattered, producibility mattered. The Soviet Union, studying both German and American tank design, chose American approaches for their post-war development. Soviet tanks emphasized simplicity, reliability, and mass production over technical sophistication. The T-54 and T-55 tanks that dominated Soviet production for decades reflected lessons from watching Shermans outwork Panthers through sheer dependability. The United States continued emphasizing reliability in post-war tank development. The M26 Pershing, introduced in the final months of World War II, featured heavier armor and a more powerful 90mm gun than the Sherman. But early Pershings suffered reliability problems that reminded American engineers why Sherman's design philosophy had proven successful. The Pershing's reliability improved through extensive testing and refinement, but the tank never matched Sherman's mechanical dependability. The M46 Patton and subsequent M47 and M48 models refined American tank design, but maintained the emphasis on reliability, maintainability, and field serviceability that characterized the Sherman. The German engineering establishment after the war acknowledged what they had known privately since 1943. The Sherman was not a sophisticated tank. Its armor was inadequate against German heavy tanks. Its gun lacked penetrating power against later German armor. By theoretical measures, the Sherman was inferior to German medium and heavy tanks. But the Sherman worked. It worked when the temperature was -40 in the Russian winter or +40 in the North African summer. It worked when maintained by conscripted mechanics with minimal training. It worked when operated by tank crews who had never touched a tank before the war. It worked, continuously and reliably, in every environment and condition. That reliability, combined with American industrial capacity, made the Sherman more important to Allied victory than any German tank was to Axis defeat. German generals could calculate that one Tiger equaled 5 Shermans in direct combat. But when the Tiger broke down before reaching the battle while all 5 Shermans arrived operational, the arithmetic changed dramatically. When German industry produced 1 Tiger while American factories produced 20 Shermans, the mathematics became insurmountable. When German logistics could not supply fuel and parts to maintain their sophisticated armor, while American logistics kept Shermans running indefinitely, the outcome was inevitable. The photographs of War Daddy II at Kummersdorf, showing German engineers examining American engineering, documented more than just a captured tank. They documented the moment German experts confronted evidence that challenged their fundamental assumptions about industrial warfare. The Germans had built better individual tanks, the Americans had built better tank production systems, better logistics systems, better maintenance systems, and ultimately better tanks for the conditions of modern mechanized warfare. Former Wehrmacht officers interviewed decades after the war acknowledged this reality with varying degrees of reluctance. General Heinz Guderian, Inspector General of Armored Troops, had written in March 1944 that Panther service life had improved to acceptable levels. That phrase, damning with faint praise, admitted that even improved Panthers merely achieved acceptability, while Shermans had been reliable from the start. Otto Carius, a Tiger ace credited with destroying over 100 enemy vehicles, compared the Tiger and Sherman in a post-war interview. When asked which tank he preferred to fight in, he immediately answered Tiger. When asked which tank was mechanically superior, he admitted the Sherman. The German experience with captured Shermans continued through the war's end. Units lucky enough to possess functioning Shermans used them as recovery vehicles, finding them more reliable than purpose-built German recovery vehicles. The last German units, surrendering in May 1945, included some still operating captured Shermans, vehicles that had outlasted German tanks built years later. The Sherman's reliability had enabled it to survive not just combat, but the general collapse of German logistics and maintenance capability in the war's final months. The strategic implications extended beyond tanks. If American industry could produce 49,000 reliable Sherman tanks while maintaining quality control, what else could they produce? German intelligence monitored American production statistics with growing alarm. The United States built approximately 300,000 aircraft during the war. They launched more naval vessels in 1943 alone than Japan produced during the entire conflict. They manufactured 2.5 million trucks, most more reliable than German tanks. This industrial capacity, applied systematically to warfare, made defeat inevitable once the United States fully committed to Allied victory. The Sherman tank symbolized this capacity. Each Sherman represented approximately 30,000 parts, each manufactured to consistent specifications, each replaceable with identical components from any factory, each contributing to a vehicle that simply worked. German tanks represented skilled craftsmanship and sophisticated engineering. American tanks represented systematic industrial production applied to military requirements. The war would prove which approach better served modern mechanized warfare. The Germans had studied War Daddy II exhaustively. They had measured, tested, analyzed, and documented American engineering. They had understood the implications. Their own engineers knew German armor could not match American reliability. Their logistics officers knew German supply systems could not sustain the tank forces Germany fielded. Their industrial planners knew German factories could not compete with American production volumes. But ideology and military doctrine prevented Germany from adapting to this reality. They continued building sophisticated, powerful, unreliable tanks in inadequate numbers until the war ended. The Americans, meanwhile, continued building Shermans. Simple Shermans, reliable Shermans, available Shermans. The tanks kept coming, crossing the Atlantic in Liberty ships, landing on invasion beaches, rolling through France and into Germany. They kept running, maintained by ordinary soldiers with basic tools, supplied by a logistics system that never failed, recovered when damaged, and returned to service within days. The Sherman won not through technical sophistication, but through consistent availability. In modern warfare, that proved more valuable than any technical advantage. War Daddy II survived the war. After its service at Kummersdorf, It was used for additional testing and training. German records indicate it remained operational through 1944, long after comparable German tanks would have required complete rebuilding. The tank's ultimate fate remains uncertain, likely destroyed in Allied bombing or abandoned as German forces collapsed. But its legacy persisted. The lessons German engineers learned from studying this single captured Sherman applied to understanding American military capability broadly. The German military had expected to fight a war where quality triumphed over quantity, where sophisticated equipment overcame numerical superiority, where tactical excellence defeated industrial capacity. They built tanks that embodied this philosophy. Powerful, complex, impressive when functioning, but ultimately unable to sustain operations against an enemy whose equipment simply worked. The Sherman was not the best tank of World War II by most technical measures, but it was the most reliable, the most maintainable, and the most producible. In total warfare, those qualities mattered more than any others. The German experts who studied captured Shermans throughout the war understood this truth. They documented it in technical reports. They discussed it in professional conversations. They watched it unfold on battlefields across Europe. They saw their sophisticated Panthers and Tigers fail mechanically while simple Shermans kept advancing. They witnessed German industry's inability to match American production while maintaining quality. They experienced firsthand the ultimate lesson of industrial warfare. The side that keeps its equipment working wins, regardless of theoretical technical superiority. When War Daddy II arrived at Kummersdorf in spring 1943, German engineers approached it, expecting to confirm their assumptions about American inferiority. Instead, they discovered American engineering that prioritized different values: reliability over performance, maintainability over sophistication, producibility over optimization. These values, embodied in every Sherman tank, represented an engineering philosophy better suited to modern, mechanized warfare than German traditions of craftsmanship and technical excellence. The Germans never matched American reliable engineering. They continued building tanks that impressed on paper and disappointed in sustained operations. They never achieved Sherman-level reliability, never matched American production volumes, never developed logistics capable of maintaining their sophisticated armor in extended campaigns. The American approach, validated by War Daddy II's performance at Kummersdorf and proven across every battlefield of World War II, demonstrated that, in industrial warfare, working consistently beats performing optimally. The Sherman embodied this principle perfectly. The legacy extended beyond World War II. Modern tank development emphasizes reliability, maintainability, and producibility alongside firepower and protection. The American M1 Abrams tank, introduced in the 1980s, features sophisticated technology but prioritizes operational readiness. The modular design allows component replacement in field conditions. The logistics system ensures parts availability before units run critically short. The maintenance doctrine emphasizes preventive service to avoid breakdowns. These approaches trace directly to lessons learned when German engineers examined War Daddy II and realized that American engineering had achieved something German sophistication could not match. The Sherman's reliability won the war as surely as any weapon system. It enabled operational tempo German forces could not match. It sustained offensives German logistics could not support. It remained available when German armor sat disabled. The tank was not glamorous, it was not technically impressive, but it worked, day after day, battle after battle, kilometer after kilometer. In the mathematics of industrial warfare, that consistent availability multiplied American numerical superiority into overwhelming operational dominance. German experts studied captured Shermans and finally understood what they faced. Not just superior numbers, but superior systems. Not just more production, but better production. Not just larger forces, but more reliable forces. The Sherman tank, examined carefully at Kummersdorf and encountered repeatedly on battlefields, represented American industrial capacity at its most fundamental level. The Germans had built better individual tanks. The Americans had built better systems for producing, maintaining, and employing armor in sustained operations. The outcome was never truly in doubt once this disparity became clear. The story of War Daddy 2 and its journey from North African battlefield to German testing ground to final obscurity symbolizes this broader truth. One Sherman tank, captured by chance, revealed to German engineers exactly what their nation faced. They studied it thoroughly. They documented its capabilities. They understood the implications. But understanding could not change reality. American engineering had created something German sophistication could not match: reliable, producible, sustainable mechanized warfare. The Germans never caught up. They never adapted. They kept building sophisticated tanks that failed mechanically, while simple Shermans kept rolling forward until Germany itself collapsed. In the end, the Sherman's greatest strength was not its gun or its armor. It was not its speed or its crew efficiency. The Sherman's greatest strength was that it worked. When German Panthers sat disabled awaiting parts, Shermans advanced. When German Tigers consumed fuel faster than logistics could supply it, Shermans operated within sustainable consumption rates. When German armor broke down from mechanical failures, Shermans kept running. That reliability, documented at Kummersdorf and proven across continents, won the war more decisively than any other single factor. The German experts who studied captured Shermans knew this. They watched their sophisticated armor fail while American simplicity succeeded. They documented American engineering approaches they could not replicate. They witnessed industrial capacity they could not match. They understood, ultimately, that they had lost not because American tanks were better in direct combat, but because American tanks were better at the sustained operations that defined modern mechanized warfare. The Sherman, reliable and available, represented the ultimate expression of industrial warfare's realities. The Germans had matched American technical capability in individual vehicles, but never matched American systematic capability in producing, maintaining, and employing armor effectively. That systematic superiority, revealed when German engineers examined War Daddy 2, determined the war's outcome as surely as any battle. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.